3.4 linear programming for Algebra 2. Let's go ahead and get started on the vocab. All right, let's take a look. So we've got draw a line from column A to the number of the vertices in column B. Pentagon. How many vertices does a pentagon have? All right, a pentagon has 5. All right. Next, a quadrilateral. Quadrilateral, how many does that have? That has 4. And a octagon. Octagon has 8. Write the letter in each vertex of the quadrilateral at the right. Okay, so 6, 4, 6, 4 coordinate. That coordinate has the name C. 3, 5, that corresponds with B. 4, -1, that corresponds with D. And 1, 2, that corresponds with A. All right, a constraint. Constraints in a linear programming situation form a system of inequalities. The graph of this system is a feasible region and contains all the points that satisfy the constraints. A constraint is a restriction or limitation. Complete the statement with the word in the sentence in its proper form. Weight is one constraint. On vehicles allowed on the bridge. An injury can cause constrained motion. The rules of a game constrain how to play. All right. Some real-world problems involve multiple linear relationships. Linear programming accounts for all of these linear relationships and gives a solution to a problem. The constraints in a linear programming situation form a system of inequalities. So a system of inequalities looks like this. All right, I have multiple inequalities in one system. All right, just like we had systems of equations, now we have systems of inequalities. Okay, we graph those, we figure out where they overlap the shade, and we go from there. This has 4 of them rather than 2. Like the one at the right. The graph of the system is the feasible region. It contains all the points that satisfy all the constraints. So that means that all of these points that are in here, all right, all of those ordered pairs satisfy every single one of those inequalities in the system. The quantity you are trying to maximize or minimize is modeled with an objective function. Often this quantity is cost or profit. Suppose the objective function is C equals 2x plus y. Graphs of the objective function for various values of C are parallel lines. Lines closer to the origin, represent smaller values of C. The graphs of the equation 7 equals 2x plus y and 17 equals 2x plus y intersect the feasible region at 2, 3 and 7, 3. All right, so those are here and here. These vertices of the feasible represent the least and the greatest values for the objective function. Okay. Linear programming is a method of finding the minimum or maximum value of some quantity, given a set of constraints. The constraints form a system of linear inequalities. The graph of the solution is the feasible region. All right, the vertex principle of linear programming. Okay, so if I look back at this example here, I have these vertices of this quadrilateral. There's 4 of them. All right, same thing in this figure here, there's 4 of them. So that means that there are 4 possible vertices to look at. In this one right here, we have 3. Okay, so those are special points we want to look at. And this is what the principle says. If there is a maximum or a minimum value of a linear objective function, it occurs at one or more vertices of the feasible region. The graph at the right shows a feasible region. Write the coordinates at which a maximum or minimum value of a linear objective function could occur. All right. So what are the ordered pairs of the vertices? All right. Well, the first one, that one's pretty easy. It's at 0, 0. All right. This one right here, that's at 3, 0. And then this green one right here is at 3, 3. Okay. So one of those ordered pairs is going to be either the minimum or the maximum value of the feasible region that satisfies the objective function. All right. And the best way to look at this is an example. So let's go ahead and do that. You can solve a problem using linear programming by testing in the objective function all the vertices of the feasible region. Okay, what point in the feasible region maximizes p for the objective function p equals 2x plus y? So here's our constraints. All right, here is our system of inequalities. Okay, so the first thing we want to do, all right, is we want to graph the inequalities. So we're going to graph each one of them. All right, now, what's special about these two right here? What's special about those? Well, x equals a number is vertical, y equals a number is horizontal. And here, they're greater than 0. So what that does is those two right there limit us to the first quadrant. All right, so we are now limited to just this first quadrant up here. So we can cross all that out. We're not doing anything over there in the other quadrants. Okay, so we're only in the first quadrant. All right, now, if we graph the other two lines, all right, if these here, we change the slope-intercept form and we graph them, they're graphed for us. So what we notice, if we shade below one of them, the red one above the blue, all right, in the first quadrant, this is our feasible region, right here. Okay? The intersection of the boundaries are the vertices of the feasible region. So that means that this point, this point, this point, and this point are all vertices of that feasible region, which is where the maximum could occur, all right, or will occur. It will occur at one of those. We don't know which one, so we're going to test it. So first, let's look at Q, all right? Q has the ordered pair 0, 0. The objective function that we have is P equals 2x plus y. All right? So I'm going to plug that in. So P is equal to 2 times our x value is 0 and our y value is 0 from our ordered pairs. There's x and y right there. Okay? So that's going to be 0. Okay? All right, next, let's plug the next x and y. So let's look at r. So r has a coordinate 0, 2.5. All right, so let's go with p equals 2 times our x is 0 and our y is 2.5. That's 0 plus 2.5, which is just 2.5. Okay, there's that one. Next, let's do s. So s is 3, 1. So P will be equal to 2 times 3 plus 1. That's 6 plus 1, which is 7. Okay? And we have one more. Let's do T, 2, 0. It's going to be 2 times 2 plus 0, which is 4. Which one gives us the biggest number? The red one, right there. Gives us 7. That's our biggest one. S. So what that means is P is the maximum value of 7 when x equals 3 and y equals 1. So the correct answer is C. So back up here, our answer is C. Okay? Question with that? Now, that particular example didn't have an application to it, but it shows you mathematically how to go about doing it. All right. Once we look at a word problem, you understand a little bit more of what we're doing. All right. But in the meantime, go ahead and pause the video. All right. And complete this problem here on your own, which is very, very similar to the one we just did. Okay, here is our objective function, p equals x plus 3y. All right, we want to graph the function. All right, so it's nice and graph for us. First off, everything's in the first quadrant again because of these two right there. That puts it in the first quadrant. All right, so I'm going to go to the right of that vertical and above that horizontal. All right, so that's everything in the first quadrant. Then I'm going below that line and above that line, and that's going to put me in this shaded region that we have right here. Okay, there are my 4 boundary points. All right, so with those 4 boundary points, let's check each one of those with the objective function. All right, so our objective function that we have again is p equals x plus 3y. Okay, all right, so let's look at our ordered pairs. All right, our ordered pairs that we have for our boundaries. The first one, the easiest one, is 0, 0. All right, that's right there, 0, 0. So I'm going to plug it in to this equation. All right, so I'm going to have p equals 0 plus 3 times 0. That's 0. All right, next, how about we do that one right there, that green one? That is 2, 0. All right, let's go ahead and plug that in. So I'm going to have p equals 2 plus 3 times 0, which will give me 2. All right, next, let's do this one right here, this blue one. That ordered pair looks like 0, 2.5. All right, so we'll go p equals 0 plus 3 times 2.5. All right, again, $2.50 times 3. Think about that mentally. I give us 7.5. And then this last one right here, all right, which is 3, 1. All right, let's see where that one leads. So p is going to be equal to 3 plus 3 times 1, which would be 3 plus 3, which is 6. Okay, so which one of these is the biggest? This guy right here. That's our biggest. All right, so p has a maximum value of 7.5 when x is equal to 0 and y is equal to 2.5. Okay? All right, so we got the procedure down. We know how to do this, but now let's look at an example of a real-world application. Actually, before that, let's answer one more question. Can an objective function p equals ax plus by plus c have the same maximum value at all 4 vertex points, q, r, s, and t? All right, is that possible? Yes. Yes, it is. Okay, at points r and s only. Explain using examples. So how about this example right here? Okay, what if I had, say, 5, or p equals x plus 3y, all right? And I had 5 equals x plus 3y. So I had 5 equals 2 plus 3 times 1. So that 5 equals 5. All right, our ordered pair we put in is right here, 2, 1. Okay. Now, imagine we did 5 equals x plus 3y again, all right? But this time I did 5 equals 5 plus 3 times 0. That's just 5 equals 5. right? What did I punch in this time? I punched in 5, 0. Okay? So what that means is this vertex of the feasible region and this vertex of the feasible region have the same maximum value of 5. Okay? So it is possible. I could have 2 different answers that have the same possible max or min. All right. Problem 2, using linear program to maximize profits. You are screen printing t-shirts and sweatshirts to sell at the Polk County Blues Festival and are working with the following constraints. You have at most 20 hours to make shirts. You want to spend no more than $600 on supplies. You want to have at least 50 items to sell. How many t-shirts and how many sweatshirts should you make to maximize your profits? How much is the maximum profit? So we only have 20 hours to make our product, our t-shirts and sweatshirts. What should we do? Should we make as many t-shirts as we can? Should we make as many sweatshirts as we can? Should we split them in half evenly? Make 50 t-shirts and 50 sweatshirts, or whatever number we have, all right? At least 50 items to sell. So we want at least those. So, but what should I do? What is my most efficient way of doing this? Well, we can do this by using linear programming. So first off, let's look at the information we have. Okay, our one color t-shirt, it takes 10 minutes to make. So 10 minutes to lay the t-shirt out, press the screen or the print, which is where the Blues Festival, the white part of the t-shirt, it melts onto the t-shirt. It takes a while to heat that on there. The supplies, it costs $4 a t-shirt, all right, and a profit will be 6. Okay. All right, next, the 3-color sweatshirt. 3-color sweatshirt information. Let's see what that says. All right, it takes 30 minutes to make that one. The sweatshirt material is thicker. It takes longer for the screen print to stick to that, so we got to melt it on there. All right, it takes longer. Supplies, it cost me $20 for a blank one. All right, and my profit for that one, okay, is going to be $20. All right, so let's write as many equations as we can from all that information. Okay, and those equations are right here. So let's talk about minutes. So the first one we have, minutes. It takes 10 minutes per t-shirt plus 30 minutes per sweatshirt, and I only have 1,200 minutes to do that. Where'd that come from? Right there, 20 hours. Okay? All right, so there's that. What other thing do we know? How about numbers? Numbers, all right? We have X amount of t-shirts, X amount of sweatshirts, all right? And what kind of inequality am I going to have for it to be 50? We want that number to be greater than or equal to 50. I want to sell at least 50 items. Okay? So we'll come back to that here in a second. Now let's talk about cost. All right, cost. It's going to cost us $4 per t-shirt to make. That came from right there. Plus, it's going to cost us $20 per sweatshirt to make. Okay? And we only have $600 to spend on supplies. Okay, so that right there has to be less than or equal to 600. That's got to be less than or equal. I can't spend more than $600 on supplies. I don't have that kind of money. And then finally, our last one, our profit. Our profit, we have $6 a t-shirt, $20 a sweatshirt. So we're going to add that. So that is going to be our objective function. Okay? So let's look at what we have for our functions. The first one we already wrote, 10x plus 30y is less than or equal to 1,200. So that's the minutes. How many minutes I have per t-shirt, per sweatshirt, and the total minutes I have until I have to make all these products. Next, x plus y is greater than or equal to 50. That's the number of t-shirts plus the number of sweatshirts has to be greater than or equal to 50. So I have enough product to sell. The next one, 4x plus 20y. All right, that's how much it costs me to make that. It costs me $4 to make a T-shirt. It costs me $20 to make a sweatshirt, and it has to be less than $600. I want to spend more than $600 to make my product. All right, otherwise I won't have too much of a profit. And then the other thing I have is x is greater than or equal to 0 and y is greater than 0. X is the number of T-shirts. Can I have a negative amount of T-shirts? No. Can I have a negative amount of sweatshirts? No. So those right there, again, are going to restrict us to the first quadrant of our coordinate plane, which means I'm going to be working with positive numbers only. And then finally, our objective function, P for profit, is going to be 6x plus 20y. All right. So what am I going to do? We're going to graph this, find where the vertices are, take the ordered pairs of the vertices, plug it in there, and figure out which one is the maximum. All right, and that will maximize our profits. Okay, so it's graphed here for us. We could do this on a calculator, on Desmos, on a graphing calculator, but it's here, it's done for us. So here is this region. So anywhere in this region are possible combinations of t-shirts and sweatshirts. All right, for example, I could make 90 t-shirts and 3 sweatshirts. Or right here, I could make 60 t-shirts and 16, or is that 14? No, it counts by 6s there, right? So I would have 15, that's 15 there. So I could have 60 t-shirts and 15 sweatshirts, okay? So those are possible combinations. I'm just gonna maximize it. So let's look at our intersection points, or vertices. 1, 2, 3, and 4. Okay, so our first one, A, is 50, 0. All right, 50, 0, that's going to be this one right here. Is this one our maximum or minimum? Let's check. So plug in, all right? So P is equal to 6 times 50 plus 20 times 0. Okay, that's going to be 300 plus 0, or 300. So I'll make $300 if I make 50 t-shirts. Okay, let's see if we do our next point, which is B. B is at 25, 25. All right, so that's this one right here, B. So let's plug in. So I'm going to do 6 times 25 plus 20 times 25. So that's going to give me 6 quarters in your hand. Get 6 quarters in your hand. How much money do you have? 50 plus 20 times 25. That's going to give us $650. Okay. All right. Next, let's check 75, 15, which is C. All right. This point right here, C. Okay. So we'll do P equals 6 times 75 plus 20 times 15. That's going to give me $750. Okay, and then our last one, D, right here, I'm going to do 120 t-shirts and no sweatshirts. All right, that's going to give me $720 profit. Okay, so look at our numbers here. Which one's the biggest? This one in red right here. All right, $750. Okay, which is C. So that means 75, that represents the number of t-shirts. So you can maximize your profit by selling 75 t-shirts and 15 sweatshirts. The maximum profit then is $750. All right. So with the time limit that we have to create our t-shirts and sweatshirts, I want to create 75 t-shirts and 15 sweatshirts. And if I sell out, I will maximize my profit. Does that make sense? Okay. All right, go ahead and pause the video. Try this one on your own. Follow through the information that's given there and complete this problem. It's very similar to the previous one, so look back at the previous one in your guided notes if you need some reference. Go ahead and pause the video and hit play again when you are finished. Okay, let's take a look. You are screen printing t-shirts and sweatshirts to sell at the Polk County Blues Festival and are working with the following constraints. You have 10 minutes to make one color t-shirt, 20 minutes to make 3 color t-shirts. You have 20 hours to make to make the shirts. Supplies for t-shirts are $4. Supplies for sweatshirts are $20. You want to spend no more than $600 on supply, and you want to have at least 50 items to sell. Okay? All right, so very similar to our previous problem. The profit on the t-shirt is $6. The profit on the sweatshirt is $20. How many of each type of shirt could you make to maximize your profit? All right, so, excuse me. Let's see what we can do. Let's write these inequalities. All right, first off, we know that those two have to be involved to put us where? First quadrant. That's got to be in the first quadrant, right? So this is going to give us 1,200, right? 1,200 hours. That comes from the 20 hours. 1,200 minutes is less than 20 hours. Okay. Here we have our 50, and here we have our 600. So we're going to the objective function that models the situation. So P is going to be equal to 60x plus 20y. Okay. Shade the feasible region. Where is the feasible region for this one? Our feasible region is right here. There's our feasible region. Okay. All right. So let's look at our vertices. One vertex is right there. All right. And that ordered pair is 50, 0. This one right here, that one is 120, 0. Another one we have is right there, which is 100, 10. And then another one we have right there, which is 25, 25. Okay. So we need to maximize this with our objective function. Let's figure out which one is going to be the best. Okay. So our objective function again is 6x plus 20y. All right. So let's use our ordered pairs. All right. So the first one we'll do is 50, 0. So I'm going to have 60 times 50 plus 20 times 0, which will give me 300. All right. Next, I'll do 120, 0, which will be 60 times 120 plus 20 times 0, which will give me 720. Next, I'm going to do 100, 10. All right. So that's going to be 6 times 100 plus 20 times 10, which will give me 800. Okay. And then the last one I'll have is 25, 25. So I'm going to do 6 times 25 plus 20 times 25. And that will give me 650. Okay. All right, where's our max? Our max is right here. Right? So how many of each type of shirt can you make to maximize the profit? T-shirts, I should make 100. And sweatshirts, I should make 10. Right? You may have thought from looking at this that it makes sense to do 25 of each. Well, it might make sense in some context, but not in the maximize your profit. All right. So it doesn't make sense to do 25 of each if we want to make the most money. If we do that, we'll only make $650. All right. If we do 100 t-shirts and 10 sweatshirts, we sell out will make $800. All right, pause the video and go ahead and do the lesson check and the math success, and hit play when you're done. All right, write a system of constraints whose graphs determine a trapezoid. All right, so we're going to write the system. Write an objective function and evaluate it at each vertex. Write the constraints to produce the feasible region. Okay, so first off, I have one drawn for us, one written for us. Y is less than or equal to 0. Or excuse me, y is greater than or equal to 0. Well, that is a horizontal line right there. So that limits us to all the positive y values, right, above the line. Okay. Now, what would the equation of that line be? Well, I'll get closer at it. It looks like it's dashed. All right, looks like it's dashed, and I'm less than that. Okay, if I'm less than that line, I know it's going to be a less than symbol. Y is less than, and it looks like it's at 2. So there's that one. Next, that line right there. Yeah, that's what we're looking at. Okay, so let's think about what that slope, intercept form will look like. I have Y. Now, where do I shade? That line right there, where's it shaded? It's shaded below, isn't it? So I know it's going to be a less than. I know it's not equal to because it's dashed. My slope, if I go start here, it's 1 over 1, 1 over 1. So it's going to be just 1x or just 1. Excuse me, 1x or just x. And if I continue, it looks like it's going to cross right there at 3. So there's that one. Okay. And then if I look at this side right here, it looks the same thing, except my slope is different. All right, my slope looks like it's opposite. So on that one, I'm going to have y is less than negative x plus 3. Okay. All right. So the function that was given us to maximize is right there. So let's test each one. All right, let's test each one. So what are the vertices? What vertices are we looking at? Looking at this vertex right here, this one, and this one. So the first one we'll look at is negative 3 comma 0. So we'll plug that in. So I'm going to have negative 3 times negative 3 plus 2 times 0. And that's going to give me 9. All right. Next, we'll look at negative 1 comma 2. All right, which is this vertex right here, negative 1 comma 2. So I'm going to have negative 3 times negative 1 plus 2 times 2, right, which is going to give me 3 plus 4, which will give me 7. Okay. All right. Next, look at 1 comma 2, which is this guy right here. All right, we have negative 3 times 1 plus 2 times 2. All right, so that's going to give me negative 3 plus 4, which is 1. And then our last one, 3 comma 0, which is right there. All right, I'm going to have negative 3 times 3 plus 2 times 0, which will give me negative 9. Okay, which one's our max? There's our max. Which one's our minimum? There's our maximum. This one's our minimum. Does it ask which one to use? No, doesn't say. But that's what we look for. We look for the max or the min depending on the context of the problem. Okay? All right, constraints. Constraints are our inequalities, all right, that form the system. All right, they are boundary lines for that region that we're looking for. Linear programming is this whole process by minimizing and maximizing profit or something else using this process. Objective function, all right, is that function that we want to minimize or maximize. And that feasible region is that overlap shaded region that all the constraints create. Put a dot in the line to how well you understood today's material. You are now all set to work on your homework for section 3.4. And I'll see you next time.